Hi everyone, welcome. Thanks for taking the time to join us today. We've got a few representatives here from the Decarbonisation Technology Accelerator programme. Bit of a mouthful, sorry, DTA for short is what I'll probably say throughout the rest of the presentation, as will my co-presenters. So just introducing them to you, this is myself, Dominique Todd. I work for the Environment Agency as a project manager on DTA. We've got Richard Walsh from Volker Stevin, Rhys Brindle from Volker Stevin, Isaac Vetnacci from Atkins Realis, and Stuart Manning from Arup. Next slide, please, Mehek. So a brief agenda for today. We're going to do a little bit of an intro to the DTA programme, talk a little bit about how we work with the hub teams, and then Richard will do an introduction to the project, to the Littleborough project. Then we're going to do a bit of a journey through the steel, concrete 2 and modern methods of construction themes and their work with the Littleborough project, and finally finishing at the end with some time for a bit of Q&A. Next slide, please. So what is the DTA? So it's a rapid tactical change programme over initially a 3-year project to accelerate the adoption of the lowest carbon solutions, materials and processes across the EA Capital programme. So why are we doing this? Well, construction makes the biggest contribution to the Environment Agency's carbon emissions. So it's imperative that the sustainable materials and ways of working become used as standard across our EA Capital programme. We want to ensure that sustainability within design and operation and construction, and that we're driving the delivery of both carbon and cost efficiency in projects. We're doing this by advancing low carbon solutions and supporting their adoption and deployment across the EA Capital programme, enabling them ultimately to become business as usual. So our goal across the 6 DTA themes is to try and reduce the EA's carbon emissions by 20% by 2030. Next slide, please, Mehek. So the DTA, as I mentioned, is progressing a range of low carbon solutions through a rigorous 3-stage maturity readiness level model, so that are progressed through testing, optimizing and scaling up. There have been over 40 solutions investigated so far across 6 focused themes. These themes include modern methods of construction, low carbon steel and alternatives, low carbon concrete, ultra low carbon concrete, earthworks optimization and asset management. And each of these themes is backed by support and industry leading expertise to help our delivery teams use the most appropriate solutions to reduce carbon in their projects. So what does success look like for the DTA? Well, this would be changing the way we all think about projects to deliver sustainability wherever possible. So a small change that we can scale up can have a really big impact on reducing carbon emissions, along with the cost and improving operational efficiencies too. So the Littleborough project, which we're going to talk about today, solutions have been used from concrete, steel and the modern methods of construction themes, trialled across the phase 1 of construction there. Next slide, please, Mehek. So the role of the DTA in the hub is to support the DTA national team and the theme leads to progress the low carbon solutions through the readiness level model, assuring that they're ready for use across appropriate projects in the EA. We do this by engaging with 6 DTA themes that I just mentioned and the hub project teams to understand what low carbon opportunities are appropriate for the project, best practice or lessons learned that can be shared. So it started off by initially pulling together a long list of projects. This has then included data gathering for case studies, identifying project opportunities for site trials, and being the link between the themes and the project teams. As projects are selected for trials, we also then work with them to develop technology scopes. So it should be noted that not all the solutions have physical trials. Some of them will be designing, specifying and learning from past executed projects, as well as gaining knowledge from the wider industry. The data gathering activity is vital to help the national wants activities, such as strengthening MTRs for low carbon emissions. The benefit of this can be realised nationally across all of the hubs and quite often more quickly than findings from site trials. Another key activity is providing specialist expertise to support the theme solution groups, which also includes wider industry sharing of knowledge. So next slide, please, Mehek. So when and where the DTA get involved in the hub projects really depends on the task. So case studies, data collection, we gather learning and best practice from completed work. Site trials and design trials, this is normally at the sort of pre-construction stage, and process trials, this could be as early as pre-SOC. So how does the DTA actually work with hubs? Well, we contact projects when an activity is needed to progress a solution and arrange initial host project meeting. We then subsequently have a theme-specific meeting with the project to determine if their project is suitable for a solution trial, a case study, or a data gathering exercise. And we work with the project team and the DTA team to develop a scope of work for that trial and agree a cost. So the next stage is to deliver that scope of work. So the project teams carry out the work, and for physical trials, DTA also visits the site. Results are captured by the project teams and fed back to the DTA, which then support and progress solution development. And in all of these cases, the DTA covers any additional costs of trialing our solution, so the over and above costs. So Littleborough Phase 1B, which we're going to talk about today in the Northwest Hub, is a fantastic example of a project which has engaged with the DTA programme over the last 2 years, and it's trialled and provided data and case studies for a range of low carbon solutions. So Richard's going to talk a little bit more now about the project.
Thanks, Dominique, and good afternoon, everybody. So yeah, I was senior project manager on this scheme, and the Littleborough project is part of the Rochdale and Littleborough flood risk management scheme, and Volker Stevin have been engaged to deliver the Littleborough element of the scheme under the CDF collaborative delivery framework. The scheme value for Littleborough is approximately 86 million. It provides significant benefits in terms of reduction in flood risk. So it better protects 337 residential properties and 185 non-residential properties. And there's also a railway that bisects the reservoir section of the site, and that as an asset is also protected by the scheme. The image you can see on the right hand side there, they're sort of all the interventions that have taken place as part of the Littleborough scheme. So the green are a previous phase 1A, which was a new bridge in Littleborough town centre and other elements of flood defence work, raising flood defences and things like that. And then the blue sections that you can see, that's phase 1B, and that's where the DTA trials were undertaken. And 1B consists of new flood defences upstream and downstream of the main element of works, which is the Gale Reservoir. The Gale Reservoir is highlighted in red on there, so you can see it's split in two by the Calder Valley Railway, and on the west side it's Gale West, on the east side Gale East, and I'll give you more details on the build in the next slide, please. So this is the reservoir. So the top left picture, that's a 3D image we did of the finished product, if you will, and the right hand picture was progress towards the back end of last year. So we've made really good progress. We've been on site now since 2024. It's a Category A reservoir, which offers a 1 in 100 year standard of protection and stores 74,000 cube of water at full capacity. It consists of clay embankments to the west and to the south, with a spillway falling into a concrete channel to the south. And then along the eastern extent of the Gale West Reservoir is a sheet pile wall. And all told, there's quite a lot of sheet piles on the project, which is part of the DTA theme that Reece will come on to later. But those sheet piles, those 2,000 tonne of sheet piles, were installed with various methods. So leader rig, Movax, and silent piler. Next slide, please. So there are some significant structures on the scheme, the main one being on the top left, which is the outlet structure. So this controlled flows, pass-forward flow out of the reservoir. So it's an 80-metre long structure, and in the middle, the sort of high point, as you can see on that left-hand drawing, there's an orifice with an orifice plate, and that can be adjusted to adjust the sort of pass-forward flow, and that's how the reservoir works, really. When flow capacity is exceeded, the water starts backing up in the reservoir. So that structure is about 80 metres long, 8 metres high at its highest point. All the structures on the site were constructed within sheet pile cofferdams with significant dewatering in place, because one of the key risks on the project was that geotechnically the site's very challenging with high groundwater. So there wasn't just sheet piles in the permanent works, there's sheet piles in the temporary works as well. However, those sheet piles have been reused elsewhere in the scheme. Then the structures on the right hand side, there's a structure in Gale East that diverts flows into the Gale West Reservoir when flows in in the watercourse on Gale East exceed a certain point. So flows from 2 rivers get passed into the Gale West Reservoir and into the outlet structure. Next slide. So apart from the structures, other significant elements of work are the earthworks and the river diversions. So the earthworks are about 5 meters high. They're quite a slack slope, and that's because of the challenging ground conditions. So they're formed on very soft clay. So the shoulders are quite slack to give a wider foundation. There's about 50-odd thousand cube of clay to import into site. That's come from a hazardous waste tip local to the site. So they dig off the clay, fill the hole they've dug out with hazardous waste, and that clay gets brought to site, and we're using that as a material to form the embankments. An interesting point to note, there's a testing laboratory on site that allows us to do all our soils testing, moisture contents and density trials on the site, and also our concrete testing, and that came in. That was advantageous with the DTA trials in terms of some of the sort of at source testing we could do. And then moving on to the river channels, there's extensive. We effectively diverted 2 existing watercourses into the Gale Reservoir, into the outlet structure. So there's 588 linear meters of new river channel formed. To encourage biodiversity and ecology, those river channels are meandering, so there's quite a complex profile, and again that brings into play the modern methods of construction that Stuart's going to talk about later with the 3D modelling, and also they're further complicated by the fact that there was bespoke gravel and rock gradings, again to enhance geomorphology and improve biodiversity. Hand you over to Reese then for the steel theme.
Thanks, Richard. And afternoon, everybody. Hope you're all well. I'm a sustainability engineer for Volkswagen. I sit on the steel team, which is headed up by Ella and Stuart Newby from Atkins and Volkswagen, respectively, and also Matthew Badger from the innovations team within the Environment Agency. Next slide, please. So, to ensure that we were targeting the correct area, the steel team conducted research early on within the DTA, and this highlighted that the majority of the steel within the EA's portfolio comes in the form of steel piles, of which sheet piles form the largest proportion. And so, consequently, the sheet piles have been the main focus of the steel team's attention. It's worth also noting that the steel reinforcement within concrete elements is being considered by the concrete team and not the steel team. Next slide, please. So the steel team identified that there should be 5 key solutions with the greatest potential to reduce carbon, and they were steel pile optimization, which I suppose can be split into 2 stages. So initially, the question that we should ask ourselves is, can the sheet piles be removed from the design and a more carbon-friendly option adopted? And if not, then the second stage would be to optimize the steel pile design by reducing the amount of steel that is necessary or that's required. Number 2 would be the use of low-carbon steel sheet piles, which we will go into greater detail in the next few slides. Number 3 would be steel reuse, so that's looking at utilising surplus or used steel rather than sending it for scrap. Better site investigations, which would improve knowledge of ground conditions and would then ultimately assist the design with being more efficient and reduce potential delays to programs, etc. There was a huge amount of crossover between the steel theme and the earthworks theme, who have now subsequently taken the responsibility of this solution. And then finally, the development of technology to understand the condition and the properties of in situ buried steel sheet piles. But we will go into more detail on number 2. So solution number 2, low carbon steel sheet piles. What are they? They are sheet piles that are manufactured differently compared to traditional manufacturing processes, but they are the exact same product. So when they land on site, you receive a steel sheet pile, and you don't recognise that there's been a change to the manufacturing process. So at present, the Eco Sheet Pile Plus range from ArcelorMittal offers the lowest carbon steel sheet piles on the market. And unlike traditional piles that are manufactured in a blast furnace, which require high energy to produce the virgin steel, these piles are produced in an electric arc furnace, so an EAF, that utilises 100% recycled scrap metal, as well as using 100% renewable energy. So this change in the manufacturing process has significantly reduced the embodied carbon of the piles. So with the industry average at anywhere between 1.8 to 2.4 tonnes of CO2 equivalent per tonne of steel, we're looking at a potential 80% reduction in embodied carbon if the Eco Sheet Pile Plus range are procured, as their EPD states a value of under half a tonne of CO2 equivalent per tonne of steel. So it's worth also noting that this only relates to the A1 to A3, so that's the manufacturing stage of the steel elements, and therefore transportation needs to be considered and assessed when completing your carbon budgets. Next slide, please. So how does this transpire to real life use on a project? So as Richard has talked about, the team at Littleborough jumped at the opportunity to procure and install the Eco Sheet Pile Plus piles on their scheme. Over 2,000 tonnes of steel sheet piles were transported from the mill in Luxembourg and installed on the project. There are a variety of methods, as Richard stated, with the pile press, the Movax, long reach, etc. And they were also installed as both permanent and temporary works. So this allowed the project team to slash the carbon budget by 2,320 tonnes of CO2. So what does this mean? How do we quantify this in real life terms? Well, it's roughly equivalent to 1,000 return flights from London to New York, which I think just represents a really substantial carbon saving. There has been a case study that's also been produced based on the use of these piles at Littleborough, so that can be disseminated at the end of this webinar, and also a promotional video, again, that can be also shared at the end. Next slide, please. So Richard, would you just be able to just give a quick explanation as to how you found using the piles on site?
Yeah, cheers, Reese. Yeah, I guess the biggest endorsement I can give is that you know the ops who were installing the piles, driving the piles, pitching the piles, welding the piles could not tell any difference between the Eco Sheet piles to a standard pile that they would use previously. Lead times are the same. The performance, drivability matches that of standard piles. At Littleborough, the cost, the piles were cost neutral. I believe there's a slight uplift now. That's due to demand for the Eco Sheet piles. And yeah, in a nutshell, there was you would not be able to tell the difference between these piles and a higher carbon pile.
Thanks, Richard. So as these piles have now been installed on a number of Environment Agency schemes, this has led to a significant proposal from the steel theme, which has then been approved by the NEIP, so that's the National Engineering Innovation Practice. A change to the minimum technical requirements, that's the MTRs, which is something that all delivery partners must adhere to, will soon state that there is a carbon cap of 660 kilograms of CO2 equivalent steel per tonne of steel on any sheet piles that are procured. And I think that this really shows that there's a huge impact that the DTA is having on future schemes, and it makes the whole DTA process feel tangible and impactful as well. It's also worth noting that this is an average cap on the steel sheet piles that are procured within a scheme, so it allows for some flexibility. So, for example, if a project needed to install some piles next week for some emergency works, for example, then piles within an embodied carbon above this cap can be used. However, the average embodied carbon for all sheet piles used on the scheme must fall under the 660 cap. I hope that makes sense. This is also in line with the 5 client carbon commitments. So if we just go back a slide, please, Mahek, sorry. It's also in line with the 5 carbon client commitments that the Environment Agency has recently signed up to, which sets a path to net zero construction. So this change allows for embodied carbon within the sheet piles to be auditable, and it also sends a signal to product manufacturers that the change is happening now and that they need to drive change within their own organizations to ensure that their products now fall underneath this carbon cap, and therefore making it possible for products to be procured and purchased. Okay, next slide, please, Matt. Thank you. So the EcoSheet Pile Plus and the EcoSheet Pile, which is essentially the same as the EcoSheet Pile Plus, but without the 100% renewable energy, are both supplied by ArcelorMittal and are manufactured out of their mills in Luxembourg. We really wanted to state that the procurement of steel sheet piles is generally considered a last resort option within the hierarchy. So as they are typically the most carbon intense solution when we compare it to alternative options. So as such, their use should be restricted to scenarios where other lower carbon options are not feasible. So to conclude, this is a really easy win for organizations to reduce their carbon footprint. It's all about a change to the manufacturing process. The product that's delivered to site is exactly the same. So let's challenge your procurement teams today. Ask them if low carbon steel sheet piles can be procured instead of the ones that are being used traditionally. Thank you. I'll now hand you over to Isaac.
Hello, hi, I'm Isaac. I'm a graduate civil engineer at Atkins Realis, and I work on the Concrete 2 theme of the DTA. Have we got the slide still? Yeah, cool. So the aim of Concrete 2 is to evaluate the processes and decisions made in projects to challenge the adoption of low carbon solutions and barriers to doing so. So we focus on low carbon concrete already within the standards, so mainly the BS8 500 concrete standard. And as you can see on the screen here, so they've got the Concrete 2 team structure. So we've got Alan Brooks as the theme lead in Atkins, and then we've got Ikram Meher and I will work as part of the theme. Next slide, please. So the Concrete 2 solution. So this theme has 3 solutions. So low carbon concrete specification, which I work on. We've got reinforced concrete optimization, which Meher works on, and C23, which is the turning mix solution, which Ikram and I work on, which is the focus here. So a key focus of all these solutions is reviewing and improving EA processes and encouraging cultural change. So the turning mix solution was the focus on the Littleborough project here, which I'll talk more about. And it focuses on encouraging more widespread use of turning mix by removing barriers and objections to it. So how concrete and cement is made. So concrete is made up of cement mixed with water, aggregates, and admixtures. Cement is made by heating clay and ground limestone in a rotating kiln, as shown in the image here. But this produces a significant amount of carbon dioxide as a byproduct. And it's also very energy intensive, as all the materials have to be heated to such a high temperature. So as you can see in the graph below as well, so even though cement is only a small proportion of the mass of concrete, it amounts to a significant proportion of the embodied carbon of it. So it's generally around 58% of the embodied carbon of concrete is used by cement. For reinforced concrete, obviously that depends a little bit on the mix used. Next slide, please. So the importance of ternary mix. So most concretes mainly use ordinary Portland cement with a small amount of ground granulated blast furnace slag, or GGBS. GGBS is a much lower carbon footprint than OPC, and so it's a popular alternative in low carbon concretes, and it does have beneficial properties as well, but its supply can be limited in the UK, and it's also often imported, so it's not always amazing for the planet. So it's very important to look at other OPC replacements that are available. So like pulverized fly ash, PFA, limestone and silica fume, which can all be used in concrete. So ternary mix is a new addition to the BS 8500 concrete standard. It was added to the standards in an update in 2023. And ternary mix includes 2 or more OPC replacements, such as these I've just mentioned, and they often can have a better availability than GGBS, and are normally even lower in carbon. And so ternary mixes in the concrete standards are normally classified as a SEM 2C or a SEM 6, as you can see in the table there. So ternary mix is a very good form of low carbon concrete that we want to encourage. And the DTA solution here has been working to spread knowledge of this and work with host projects to trial and use it and encourage more widespread use of the mix. So next slide, please. So on the River Roch Littleborough project, this was a key host project for the ternary mix solution. There was a significant use of ternary mix here, which saved over 12 tons of carbon dioxide from an already lower carbon concrete specification. The ternary mix was used across this phase of the project on all the key structures, which are listed on the slide here. What they did was they pre-blended limestone fines with OPC, and then they delivered to a silo closer to the site to mix with the GGBS. So you've got your ternary mix there with OPC, limestone fines, and GGBS. And it was a great chance for a large-scale trial of ternary mix and to gain experience using it and lessons learned. And also a case study was produced about this as well to also spread awareness and knowledge of this concrete mix. So next slide, please. So the lessons learned. So this trial use of ternary low carbon concrete on the Littleborough and Rochdale flood risk management scheme, phase 1B specifically here, provided a number of valuable lessons that are relevant to future Environment Agency projects and all projects really. These lessons relate to specification and design, construction and delivery, and quality assurance monitoring. So the key theme is that early engagement between the client, designer, contractor, and concrete supplier is critical when proposing a high SCM or supplementary cementitious material concrete, or ternary concrete mixes is an example of those. This enables performance requirements, durability criteria, and carbon objectives to be aligned and agreed on prior to construction. This kind of thing can even be added into contracts as well. And so this trial demonstrated that a meaningful carbon reduction can be achieved at a relatively low additional cost from the concrete, and that additional cost was covered by the DTA program as part of our works. But the plan is that in future ternary mix and other low carbon concretes, the cost will come down as they become more widespread and more widely available. And hopefully eventually they will actually become cheaper than standard SEM 1 concrete because they often use sort of waste products and byproducts of other processes. So next slide, please. So MTR compliance. So the ternary mix incorporated SEM 1, which is an OPC cement, GGBS and limestone fines to form a compliant ternary binder that meets the BS 8500 concrete standards and the latest update of the EA minimum technical requirements, V12. We used the agreed option 3 benchmarking approach, where performance was evaluated against both a traditional SEM1 baseline and the EA standard SEM3A and SEM3B mixes. Key findings indicated that the ternary mix achieved a low embodied carbon, with roughly about an embodied carbon of 128 kilograms of CO2 per meter cubed, which is a massive reduction over standard SEM1 concretes and other concrete mixes. It delivered a satisfactory structural performance, offered acceptable workability across all the pores on the project, when supported by curing and maturity monitoring. So it was a very successful deployment of ternary mix here on the project. So thank you, and now over to the MMC theme.
Thanks, Isaac. Well, good afternoon, everybody. Hope you can hear me okay. I'm a design manager at Arup, and I'm the consultant lead on the modern methods of construction theme on the DTA programme. We'll call it MMC rather than the full modern methods from here on in. So MMC has got a range of solutions. The sort of first two, and the first one I'll talk about primarily in a moment, but essentially the top two are more about site technology with the digital input, and then how we make the best use of kind of digitally minded technologies during construction. And then the latter are focused on different ways of fabricating structural and other components using the efficiencies of manufacturing off-site, or in the case of 3D concrete printing, whether we can actually have robotic printers creating components near to site. So hopefully we'll be able to share more on those and trials in the not too distant future. Today we'll talk about 3D machine control and how it applied to the Littleborough project. So 3D machine control, some may have heard of it, it's been around some time. It's a modern construction technology that enables accurate control of the machine equipment, particularly the bucket and the arm and the blade level, position and orientation, essentially giving the driver a display, as you can see in the cab in the photo, and an ability to control that equipment with feedback from where the equipment is positioned relative to the model that they're trying to achieve. That's done via sensors on the arm and the bucket, and either a GPS-based system or in some cases using a total station to control it, or that's far less common. It's also known as machine guidance in that case as well. Machine control could be essentially manual, so all control by the driver, but just with the digital display prompting the construction, or semi-autonomous, where, for example, the blade or the bucket might angle itself to match the grade, and the driver is more moving the arm as an example of that, but there are different forms. Or fully autonomous is out there technically, but it's more of a future possible technology where the driver, if they are still in the cab or remotely, can be making sure the machine is doing what it does, but ultimately there is sort of almost sci-fi type version of this where the machine is able to work from a model, but obviously there's various downsides and safety considerations before we contemplate that outcome. So the focus is, of course, on the manual and semi-autonomous for the sake of the DTA and also scaling up objectives. One important part of this is the 3D model being available for the construction team to deploy into the machine. And so we're considering this as more of a process than just a site technology, and looking at how 3D design data is making its way to the construction team and what we could be doing to smooth out that process, informing the designers and the project managers before even in construction about what 3D data is likely to be needed, understanding where machine control would tend to be deployed for the types of projects they've got coming up, and making sure that they're including in the scopes and the process for giving that information. I'll say a bit more about that a bit later. We're also looking as part of that kind of middle box in the process to understand what steps could be taken to verify that data before the machine is digging away with the surface or the design strings, particularly where there's kind of coordinate system conversions needed to get it into the site system. And then finally, of course, understanding the various benefits and efficiencies and any possible hiccups in the use of it in the machines. So we've done other trials where we've observed sort of signal connectivity and downtime issues and how they could be mitigated to keep the construction moving swiftly and mitigate against any possible sort of GPS or other problems that can occur in the technology. Next slide, please. So in terms of the Littleborough trial, this was specifically aimed at assessing how well 3D machine control works in the case of the river diversion channels that Richard mentioned a little while ago. So you may recall the different parts of the reservoir scheme on the west and the east side of the railway. The west channel was done significantly before the trial came around, and that was done with more traditional methods without a 3D model. And then we saw the opportunity ahead of the Gale East section to do. So I think the text is a bit different to what I said there. Apologies, but yeah, for the Gale East section we did use the 3D machine control with the model, and then measured the differences. What was the program and the fuel across both those sections, and tried to draw conclusions about the efficiencies that machine control achieved. We also went to site and spoke to the machine driver and Richard as well, and just talked about how well the model played a benefit. And we particularly observed that the complexity of the shape of the channel geometry and the sort of curving, sort of nature-friendly or aesthetically pleasing curving river profile was particularly favourable to then use the 3D model because the setting out would have been quite complex. And so there's sort of benefits around site engineering as well. And some of the results are there on the screen. I'd say, modest figures compared to the excellent carbon savings that the steel sheet piles achieved, but other benefits such as sort of safety and having less interface of site engineering staff having to go and check and set out in proximity to machine equipment is an important benefit that we're hoping to see more of as this sector gets scaled up. And it was good for us to see that it is a positive experience of using the technology for this channel use case, which is less common. Go to the next slide. So I'll just talk about a couple of the kind of overall lessons learned for the technology, and then I'll ask Richard to come in to sort of comment on some of the site observations. So the sort of top two are really about recognizing this is a well-established technology on the larger scale earthworks, but we do believe there's potential for wider adoption of it to sort of channels and other small use cases that you tend to see on flood risk management schemes, particularly if the models are readily available and the process is very smooth to deploy it and it's been de-risked. And that's our objective ahead of trying to scale it up for future schemes. And then other trials are showing, like I said before, really the importance of having a good signal or providing suitable base stations across the site to make sure that signal to the GPS equipment is maintained and you are getting the efficiencies that you hope to achieve. And I'll ask Richard to come in there about how it went on this site.
Yeah, cheers, Stuart. Yeah, so just to reiterate some of your points you made, really. So we always intended to use 3D modelling for the embankments, because that's sort of traditionally what you would do. And we were less clear what the benefits would be with the river channels, but having constructed a significant portion using traditional means without the 3D machine control, it was clear that it could only help us out, and it did. As you can see there, it's quite a meandering channel, quite complex to set out. So traditionally, we had an engineer there pretty much full time. So to reduce that engineering interface was massive from a cost and also from a plant people interface perspective, and modest gains in terms of carbon, but much more efficient way of doing it. I'd say there's the feedback from the driver, as with anything, any sort of new gizmos that you get to work with, it probably took him about a shift or half a shift to get used to using the technology. But after that, really good feedback from the driver. That's what that's probably the best feedback you're going to get, the actual the ops actually delivering the work. So yeah, worked really well.
Excellent, thanks so much. And the last thing I'll finish on is the recognition that the sort of modelling for this in the trial case was done by the construction team, and we are looking into whether, through the design process, the models could be available immediately to use without further modelling. But it was interesting to see that modelling could be done by different parties and still get the technology delivered. And then it's over to Rhys, I believe, for the sort of call to action.
Thanks, Stuart. Yes. So I suppose the big question: how can we make these solutions business as usual? It's a bit of a call for action, a call for arms. So let's increase the awareness of already available products. So these products are already in the market. We're not talking they are super revolutionary and difficult to get hold of. They are there. Let's go and get them. Let's increase that awareness of them. Let's challenge our procurement teams. So let's make sure that our procurement teams aren't always aren't going back to the supplier that they've been using for the past 20 years. Let's challenge them. Can we push their boundaries to not only find products that are financially viable, but also carbon friendly as well? And then I think Isaac touched on it in terms of if we increase the use, then that would then bring down the cost, so just economies of scale. And we're also looking to introduce guidance and run webinars to support the teams and help them understand when in a project's timeline solutions should be considered. So Stuart, for 3D modelling, for control feedback, is that it needs to be considered when scoping the scheme. It shouldn't just be considered during the construction stage, as this may be too late in the project. And that's it. So Dominique, would you like to close out?
Yeah, thanks, Rhys. So just finishing with this slide, which is how you can contact us. If you want to find out anything more, you can email us, and this is our email address at eadta@environmentagency.gov.uk. There's also a live link there to our DTA SharePoint page, so we can have visitors to that site. We've got a lot of information on there about the different solutions and some case studies, videos that you can watch. And the lower link, contact your DTA hub team, takes you to a link of all the contact details. So for each hub, obviously we have different hub leads, and we have all the theme people. Some of them you've met here today. A huge team of up to 200 people working on the DTA program. So but we can point you in the right direction. If you've got any questions, just send them through to us. So just to finish off, if we've got any questions, we're happy to take them. So open the floor to anyone who wants to ask anything. I think there's been some questions in the chat, and I think people have been answering them as they go along. If we can't answer them all today, we will follow those up and get back to you. Great. If no one's got any questions for us, hopefully we did a good job in the presentation. Don't know if any of the other presenters have got anything else they want to add, or from the chat questions.
Anything to add, I think, Dominique, is that although some of the attendees may not be Environment Agency or direct suppliers on the CDF, we're hoping to sort of collaborate across the infrastructure sector. And obviously some council projects could be using the CDF framework, but we're also talking about completely different aspects of infrastructure where the solutions might apply. So we're quite happy to be hearing from people working on other projects where some of these technologies could be coming in. So feel free to reach out outside of this meeting.
Great, thanks, Stuart.
There's nothing else from myself. Dominique.
Okay.
Thanks, everyone.
Yeah, thank you, everyone. Thanks for coming.
Okay.
Yeah, thanks.
And this has been recorded, so feel free to share. Thanks so much.